Kuzuzangpo, Bhutan e-learning welcomes children to this lesson. I am Sushmika Tamang. This lesson is a physics lesson for Key Stage 5, that's for classes 11 and 12. So children, I hope you all are studying at home, and at the same time I hope you are helping your parents in doing household chores like doing dishes, watering the plants, doing gardening, and I am sure you must have done this while watering the plant, especially when the plants are far away, you can't reach, so you do this, right? Have you ever wondered why you do this? Okay, let the scientist in you think harder. The reason is because of equation of continuity. Here you can see there is a pipe of different dimension. The bigger one has area of A1, and here the water is flowing with velocity V1, or any liquid is flowing with velocity V1. The other end has a smaller dimension where the area, cross sectional area is A2, and the water flows here at the velocity V2. Now according to this equation, it says that the volume of liquid in the A1 for a given time, if it enters, then same volume of liquid should be coming out of the other end. So with that we have A1 product of area times velocity at one end will be equal to A2 times V2, product of area and velocity at the other end. So this means that product of area and velocity at a given time over any cross section remains same. So therefore I can generally write A times V, area times velocity at any cross sectional area at a given time, to be constant. We can write constant as K. So then we have AV is equal to K. I can take V to the other side, so it will be K over V. Now if I remove the constant, I will have to introduce a proportionality sign, which would be 1 by V. So then this is very clear. It means if the area is more, velocity is less. They are inversely related. That is why when you squeeze the water hose, the area decreases and the velocity of water increases, so it reaches further away. So that is how it works. Now let's put this in practical situation. See here, you can actually make your own water sprinkler in your garden. You can do that now. You can see there is a water hose, main pipe, and it is connected to a bottle with lots of holes. So here you can see the water hose has area of A1, cross sectional area of A1, and the velocity of water in that hose is V1. And in this sprinkler, let us say you have made 10 holes and water is coming out of that hole at a greater speed, you can see that. So there the area of each hole is A2 and water is coming out at velocity V2. Now if you want to find the velocity, we can actually use the equation of continuity. So by that we have, so A1 times V1 is equal to A2 times V2. Now since there are 10 holes in the bottle, in the sprinkler, so the volume of water entering should be equal to volume of water leaving. That is why you multiply by 10. Now let us, since you are asked to find velocity V2, let us make V2 the subject. So when you make V2, this is the relation that we get. So now area A1 and A2, the area is, you know, it is a pipe, so it will have a circular dimension, which means area of a circle. So area of a circle, you know, it's pi r square. So let us take the radius of the pipe to be r1 and radius of the hole to be r2. So we are replacing A1 by pi r1 square, A2 by pi r2 square. Now pi and pi will be cancelled and we will substitute the values. In the question it is given that r1, the radius of the pipe, it is 0.02. So we are replacing that. So velocity is 2 meter per second in the pipe, and then replacing the value of r2 R2, which is 0.0025. So, when we replace that, we will get the value of velocity of water coming out from the holes, which is 12.8. So, this clearly proves the equation of continuity. You can see at much greater speed water is coming out of the holes. Okay, this is one practical application. Actually, you see this in nature all the time. See, you can see the stream is small, the river is narrow, the speed of water is high. You have actually seen this, but you may not have been mindful enough to remember it. So, here you have a wider river will have lesser velocity. So, there are lots of things where you see things which is related to equation of continuity. So, now we have learned that if velocity increases, area increases, or if area increases, velocity increases whenever there is flow of fluid. What do you think will happen to pressure? Pressure is another thing. What do you think will happen to pressure? Now, to understand that, let us look at this picture. This we see all the time, especially during summer and autumn when there is a storm or a heavy high speed wind, then you see the roof being blown off. Why do you think this is actually happening? Now, to understand how the pressure changes, we will take this diagram, okay, take this situation when the roof is blown off. So, let us say this is the roof of a house and there is a heavy storm or high velocity wind flowing. So, here the velocity is V1, high velocity. So, compared to this, inside the house naturally the velocity is less. So, I will write V1 is much greater than V2. Now, whenever at a point if the velocity is more, pressure is less. So, let me assign here P1 pressure, assign here P2. So, whenever, again I repeat, whenever the velocity at a certain point in the flow of liquid, if it is more, pressure is less. So, P1 is lesser than P2. So, this inner pressure which is high will create upward force and it will be blown off. So, that is the reason why the roof is blown away whenever there is a heavy or strong wind blowing. So, so actually this idea, this concept was first discovered by a scientist named Daniel Bernoulli. So, Daniel Bernoulli, he discovered and he made a principle called Bernoulli's principle, which says that whenever there is a streamline flow of liquid, if the velocity is less at a particular point, then pressure will be more. So, that was his principle. Now, this is the actual statement of the principle. I will read it out. According to Bernoulli's principle, for a streamline flow of an ideal liquid, the total energy, which is equal to sum of pressure energy, potential energy and kinetic energy of the liquid per unit mass, remains constant at every cross section throughout the liquid flow. Did you get it? Complicated, right? But actually it becomes much easier with this mathematical understanding. So, you can see in this diagram you have a pipe of different dimension. The lower one, which is closer to the ground, which is at H1 height. So, H1 is the height. So, the bigger pipe has the area of A1, cross sectional area of A1, and then here in that pipe the velocity of the liquid is V1. At the other height where the dimension is smaller, the height H2, that is the height, and the dimension of that pipe is A2, which is smaller, and here the velocity is V2. Now, from the equation of continuity, we know that V2 will be greater than V1, that we already know, right. So, according to the principle of Bernoulli, it says that total energy at, let us say, the lower end, total energy, which is the pressure energy, kinetic energy and potential energy at this lower end is same as, or the sum is equal as that in the upper point. So, pressure energy, kinetic energy, potential energy at the lower end is equal to the same pressure energy, kinetic energy and potential energy at the upper end. Now, this further, if it is simplified, the Bernoulli's principle, when it is further simplified, it becomes like this: P1, which is pressure at end A. So, this actually represents pressure energy, half times density V1 squared. So, D is the density of the liquid, V1 is the velocity at the lower end. So, this whole represents kinetic energy plus the potential energy, which is H1 density, which is rho, represented by rho, times G. So, this represents the potential energy. So, sum of this at the lower end is equal to pressure energy, kinetic energy plus potential energy at the upper end. So, I will repeat the law: the sum of the energy per given volume or per given mass over any cross sectional area is remaining same. So, generally also we can write P1 plus, at any point it remains same. So, it will be P plus half density V2 square V square plus H density G, whole thing is a constant. So, we can even express mathematically Bernoulli's equation like this. Okay. Now, let me show the simple principle, that was when when velocity is more, pressure is less. Simple thing we will explain using this, which looks quite difficult, equation. Okay, we will come to this conclusion from here. So, for that, let me take a pipe. This time the height I have taken same. Here also let us say H1, here also height is H1. Here let us say pressure is P1, here the pressure is P2, and here the velocity is V1, here the velocity is V2. Now, from equation of continuity, here the area is more, velocity has to be less. So, you can write V1 is less than V2. Now, we will apply this concept here. Okay. So, let me rub this. From this equation, so P1 is here, half density V1 is this one, then H is for this one, for this side, and the rest of the thing is for the other side. Now, since height is same, height is same, height is same. So, replace 2 by 1, height is same, density of the liquid is same, acceleration due to gravity is same. So, this value is same. So, this will be cancelled. Now, again, half and density for a given liquid is a constant. This is also a constant. So, I am neglecting that. So, I am just writing P1 plus V1 square, okay, is equal to, sorry, this is P2, P2 plus V2 square. So, this is what we have got. Now, here V1 is less. So, let me write V1 as 5. Since it is square, I may square it. V2 is more. Let me write this just as an example, 10. So, 5 5s are 25 is equal to 10 10s are 100. This 10 square is 100. So, here now P1 and P2. So, now the sum has to be equal. So, here if I write 100, here if I write P1 as 100, then how much should be P2? It should be 25, right? So, here clearly if velocity is less, pressure is high. If velocity is more, pressure has to be less. So, this is clearly understood by this expression. So, whenever you have higher velocity, pressure is less. So, this is coming from the complicated equation and then coming to the same conclusion that pressure increases with the decrease of velocity. Now, there are lots of applications of Bernoulli's in real life situation. One is this one, Bunsen burner, which you use in chemistry lab. So, here if you look carefully, you know how it is used. You have to connect the pipe here, gas will come out and then it will burn from here. Why do you think there is a hole here? Don't you think gas is going to get leaked from here? Okay, the reason here is because of the Bernoulli's principle. Now, let me explain. So, when gas pipe is connected, it will enter with very high velocity and it will reach here. But you know, for the gas to burn, it needs oxygen. So, the gas has to mix with oxygen and then combustion happens. But if the oxygen is not enough, then the gas will not burn properly. So, for that reason, when this hole is made, so when the gas enters here with very high velocity inside, when the velocity is high, pressure will be low. So, pressure is low. Now, outside the pressure is high. So, that way the outside air will gush in, it will get in from this because of high pressure and here there is low pressure. So, it will get in and it will get mixed with the gas and then it will burn properly. So, that is simple application of Bernoulli's principle. Now, I am going to show one more demo of Bernoulli's principle. You see and let me know the reason, okay, or you may explain to yourself the reason and check with my explanation later. See? Why do you think this is happening? When you make the dryer on, the high velocity air rushes in. So, this is the ball. Let us check whether your explanation and my explanation are similar or not. So, here there is high velocity, low pressure. So, low pressure here and this side. So, here also it will be higher velocity, so low pressure, but above this side there will be atmospheric pressure which is higher. So, therefore, because of the pressure difference the ball floats in the air, okay, it remains in the air. So, that is another explanation of Bernoulli's principle. You have seen, we all know that the water tanks are usually kept at the top building top or either at the high heights like in mountains and all that. As you can see in the picture, it is kept at a very high height and this is again because of Bernoulli's principle. Now, we will see with what velocity the water comes out from this water tank. Okay? Let us say this is the water tower, let us say, and water is still here. Let us say its height is h1 and there is an opening or orifice here, opening from where the water is coming out. So, you know to reach to different areas the water coming out should have very high velocity. Let me write this as V2. Height here, let me write h2 and you know it is at the ground level. So, h2 I am going to take it as 0. Pressure here P2, pressure here P1, velocity here V1. Anything else? That is all right. So, now practical application of Bernoulli's principle comes here also. We just want to check with what velocity the water is coming out from this opening. So, it is the general principle, half density V1 square plus H1 dg P2 plus half density V2 square plus H2 density g. So, this is for the upper height here, pressure P1. Now, since this is open, we are going to take pressure because pressure due to atmosphere. We call it atmospheric pressure. So, let me write it as PA. And now the volume of water is so much that the velocity with which it flows is negligible. So, therefore, V1 I am going to assign 0. Okay. So, then whole thing becomes 0, we need not write, and this one is same height is H1, density and G is equal to P2. Now, here P2 also, it is coming out in the atmosphere. So, this is also atmospheric pressure. So, let me write it as PA plus half density V2 square plus H2. Height here is the ground height, so it is 0. So, if height is 0, the whole thing becomes 0. So, if I do not write also, it is fine. So, this much we have. Now, pressure, atmospheric pressure and atmospheric pressure gets cancelled. Now, we are finding the velocity at which the water comes out from this opening. So, then we have H1 density G is equal to half density V2 square. Density and density gets cancelled. We can take 2 to the other side, it will be 2 H1 G is equal to V2 square. So, to remove the square, we can take root both sides. So, we have 2 H1 G and the root is velocity. So, this is the velocity at which the water comes out. So, see here, velocity is directly related to height. Higher the height, more the velocity. So, for that reason, the water tanks are usually kept at a very high heights, like in the top of the building, okay, so that it comes out with greater speed and reaches most of the areas. Okay. Now, we will have another activity, and this time this activity I will use POE, which means you will first predict what will happen in this activity, you will observe and you will explain what you saw, you will explain the reason to yourself, and I will explain mine, and then let us compare whether you are right or not. So, here I have a paper which is folded in shape of V, and I am keeping it here, and here is a pipe. So, now I will blow air inside this, okay, inside this V shaped paper. So, what do you think will happen? Have you done prediction? Okay, now let us see what actually happens. So, what did you see? The paper is becoming flattened. Now, what is your explanation? Okay, let us check whether your explanation is correct or not. So, this is the paper, you are blowing high velocity wind inside. So, V1 is high, P1 will be low. So, pressure inside is less, atmospheric pressure outside is more. So, that will press down, that is why it becomes flattened. So, that is the reason. I hope you got the same reason, and if you got it correct, very good. Okay, now quiz time. You can see there are two pictures from what we learned today. Equation of continuity, Bernoulli's equation or principle. Can you tell me whether diagram A or B is correct? You can read the question. So, you have incompressible non-viscous liquid flowing. Which of the two figures is incorrect, or which one is correct? A or B, which one is correct? I will give you 10 seconds. Okay. Now, let us see whether you have got the correct answer or not. So, let us see the first one. In the first one, A, you have ideal fluid flowing here, the water level is here. In the first tube it is lesser, in the second tube it is higher. Now, let us see, here you have bigger area, lesser velocity, more area, less velocity, more pressure. More pressure means it will push the water up. So, naturally the first one is wrong. It should have been B. How? B would be the correct answer, because here more area, less velocity, high pressure. So, more liquid will be pushed up. Here less area, more velocity, less pressure. So, not much of liquid will rise up, right. So, the correct answer is B. Now, as I said, there are lots of areas to explore, and you can see that yourselves whenever you go around and explore where you see Bernoulli's principle. Like in prayer flags, actually you see Bernoulli's principle, but I will give you some areas to explore. The one is airplane. What or how is Bernoulli's principle explaining the flight of aeroplane? Another one is, if you are a sports person, if you are very good in cricket, what principle, I mean how principle of Bernoulli will help you be a better bowler or spinner. So, all these are few areas to explore, and you can explore more. Okay. So, that is all for today. I hope it was clear, the lesson was clear. Thank you for attending this lesson. I will see you all in the next lesson. Thank you.